Francisco Carais and Rodrigo Pimenta, postdoc at the time. Now he's a faculty member, professor in Federal University of Rio Grande do Sul. Actually, the title of this talk should be said to be a method for computing the mass gap of free fermionic quantum systems. But I prefer this title, a series of fortunate events. And I hope by the end of this talk, why I put this title, this should be clear. Okay. So I start with a motivation. I introduce a model that we're working on. And then comes a polynomial that allows us to compute the mass gap. I will tell you how to use this polynomial and devise a method, efficient method to compute the mass gap, which scales linearly with the system size. And then I will show you some applications to clean systems and to the random process field using chain and another model that I will introduce called the Randolph-Findlay model. All right, why study free fermionic quantum systems? Well, it gives us some exact results, so it's reliable and it can be used as test bed for new ideas. It exhibits also interest in complex behavior like quantum phase transitions, fractionalizations, Anderson localization, Griffith singularities, and many other interesting phenomena. So let's see what they can teach us. All right, so very basic. What's a free fermionic quantum system from the undergrad stat mech? Is that sort of systems that you have energy levels and you can put a particle or remove a particle, and these energy levels, the values of them doesn't depend on how many particles you put there. So I just rewrite this in a different, I multiply by 2 and divide by the sum of these epsilons. And the Pauli principle is said to be you put either particle here or there, so there is one particle per circle. All right. So that's the model. We have a generic model. H is an operator, and lambda is some coupling constants. And these operators, they obey this algebra. They if they are close together, and they commute if they are far, and P is a parameter of this model. So if we, for instance, think of n equal 2, this omega is -1, so they anti-commute if they are neighbor operators, and they commute otherwise. For other values of P, then anti-commute until some distance, and so until distance P, and commute otherwise. Okay. So n equal 2, P equal 1 is the famous transverse field using chain. So I rewrote it like this here. So lambda 1, the transverse field, and so on. And the conventional solution for this model is textbook. You map to free fermion via Jordan-Wigner transformation. That's the transformation here. These fermionic operators, and the eigenenergy, you just fill up your Fermi C. So the quasi-energies are eigenvalues of a L by L matrix, and that's well, very easy to do. Okay, so n equal 2, now P equal 2. That's the Findlay model. So it's a three-body interaction. So this guy anti-commute with that and that, but commute with this, and so on. There is no Jordan-Wigner transformation for this model, but however, there is a free fermionic spectrum. You can find all the eigenenergies of this model just filling up the Fermi C, and putting fluctuations on, putting excitations on top of that. So, and I'll tell you how to find this quasi-energy is a root of a polynomial of degree L. And let's find this polynomial. So n equal 3, now you get complex numbers here. This is the maybe famous, I don't know for how many of you are acquainted with that, but that's the called Baxter chain. There is a representation for this model, and is given by this matrix here. And the spectrum it has complex energies, so you could think as this a generalization of fermionic statistics, like it's called parafermionic statistics. So you get a parafermionic spectrum. And for lambda equal 1, these the eigenenergies are these epsilon k's that I wrote here, and it come out from this polynomial that I'm going to tell you later. Okay. Let's see how do we find this so-called polynomial that I'm telling you. So comes the fortunate event. So the first fortunate events is to find an extensive number of conserved charges in evolution, meaning that they form a complete set of commuting operators. And the first charge is the Hamiltonian itself. The second charge, you get those H's. Now H, I just multiplied by lambda here. So this H, the second one, you multiply one H by another H, but they have to be farther apart than P. And the same for free operators and L operators. So they have always to be constrained that they are not anti-commuting. You have just commuting operators. And they form a complete set. And well, that's a fortunate event. And you'll be fortunate later. But we can define this generating function for these charges, these conserved charges. All of them, it's a tedious algebra, but all of them commute with the Hamiltonian, so they are conserved charges of the system. Okay, there comes the second fortunate event. It's to find an inversion formula. What's an inversion formula? Is the following. You get that function g multiplied by g minus 1, and well, there are tons of operators in this g here, but they conspire to be a scalar. So there is no operator on the right side. So all the operators conspire, and you get the identity matrix. This is for n equal 2. For n equal 3, you have to do this combination here, and so on. Since this is a polynomial, we know that any polynomial can be written as a constant times the argument of the polynomial minus its roots. So ui is the roots of the polynomial. And so we have a polynomial here and a bunch of operators there. Okay. The third fortunate event, and they all come together later on, is that the roots of these polynomials are the quasi-energies. And how can we see that? Well, we start with the left-hand side of that equation, and well, just to do the algebra, and you see that the first term of this polynomial is 1 minus something that is proportional to the Hamiltonian to the power n, and if you apply it on an eigenstate of the system, you get the energy to the power of n. All right. Now you go to the right-hand side of that equation and expand this polynomial, and then you see that well, I just rearrange here how I wrote the roots, but you get this coefficient for power u to the n. So since these polynomials must be equal, e to the n is the sum of the roots of the polynomial to the power minus n, and sum of them together, and then you have to solve for this equation. And then you have to convince yourself, it takes a while, but after the solutions of this equation is the following. So it's the same. Form that we have here for these free fermions problem. Meaning that we just found the quasi-energies of this polynomial. I mean, the quasi-energy of the Hamiltonian, which are the roots of the polynomial. All right, so you get the roots put to the power -1 over n, and that's the quasi-energy. Okay, so I will show you now a method to compute this polynomial that is efficient, and let's see how it helps us to compute the mass gap. So the polynomial is this one here, and it can be computed by recurrence relation. When you add one more operator to the next, you can see that the next polynomial depends on the previous one times something else. Before the polynomial, previous polynomial already computed. So computational time is of order L square. And for translational invariant systems, all these coupling constants equal to 1. I just put here these polynomials. So for p equal 1 and p equal 2. And all these coefficients can be computed analytically. They grow factorially fast with L. So, okay, so you have a big polynomial, with big coefficients that grows factorially fast. And so what's good for? If you want to put in a computer, very soon you run out of memory because you cannot stack numbers that are very far apart. And so what? How about in homogeneous systems that even in homogeneous systems you don't have an analytical formula for the coefficients, but we can use the recurrence. All right, then comes Mr. Laguerre, the same Laguerre from the Laguerre bound. For the Laguerre polynomial that we are very fond of. And he gave us a theorem that I was not aware before working on this problem. And the theorem is the following. If you have this polynomial with real coefficients, he says that all the roots of the polynomial will be bounded. So by this number here, U Laguerre bound, which is this number here that depends only on the 3 last coefficients. The coefficients L minus 1, L, and L minus 2. So this theorem is something very how do you say, outstanding. How can we bound all the roots of a polynomial knowing only the 3 last coefficients of this polynomial? All other, there are many bounds if you go to this book here. There are many bounds on the roots of these polynomials, but all of them involve all coefficients except for the bound of Mr. Laguerre, which involve only 3. So this gives me some hope, because now I can look only on the 3 last coefficients and know more or less where the roots, at least the last root. And the last root actually is the most important one, because the quasi-energy is the inverse of the root of the polynomial, meaning that the largest root is the smallest quasi-energy, and the smallest quasi-energy is the mass gap. Okay, so you have a Laguerre bound, and when is this useful? And let's go to the 6th fortunate event. It's useful for gapless systems, because we are looking for the mass gap, which is the minimal quasi-energy, and this is the maximum, the largest root, and the largest root is bounded by the Laguerre bound. And in gapless systems, if you increase the system size, the mass gap goes to zero, the finite size gap goes to zero, meaning that U is diverging. So U is diverging, so the Laguerre bound also must diverge. And then luckily, then comes another fortunate event, is that this Laguerre bound is very close to the actual largest root. So it's very fortunate that happened. Then comes the next fortunate event, and these pointer lasers dying out, is that for computing this largest root, since the roots are all spreading and they're getting far away from each other because the system is gapless, so the inverse of it is getting far and far apart, we don't need the entire polynomial to find the largest root. We just need some part of the polynomial. And therefore, we don't need the entire polynomial. To compute the polynomial efficiently, we only need some number of coefficients, and this can be done with computational cost of order of the system size. So it's linear with the system size. So this method works better for critical systems, which is complementary to what's available in the market. Usually, what do you do to compute the mass gap? You get the Hamiltonian, do exact diagonalization, compute it. And this is very efficient if the correlation length is small, because then you don't need to go to large system size. But here is the other way around. It works better if the gap is vanishing, so the roots separate from each other, the inverse of the roots separate from each other, and we are better suited. Okay, so the method is the following. We compute the polynomial recursively, keeping only a few coefficients of order 30. We keep 50 in the paper, but 30 is well enough. That's the recurrency for computing this polynomial. We don't need to compute all the coefficients, so this cost of computational time of order L. We compute the Laguerre bound, then and use it as a starting point for Newton's method to find the largest root of our truncated polynomial. Don't need the entire polynomial. So we consider different L's and find the dynamic exponent via brute force. So you can compute this exponent there. So let's apply this method to Fendley's model, which is this model here. And if you get these three parameters, A, B, C, and B, C, and so on, this is the phase diagram. There is three phases, this gapful phase, and three transitions, and one multicritical point. And this multicritical point has Z 3/2, and these red lines here are in the easy universality class Z = 1. So this can be done, can be shown by our method. We can compute the mass gap. So here's the mass gap, and the Laguerre bound can be also computed. What is the Laguerre bound? You compute the Laguerre bound, which is very close to the root, and consider this the gap due to the Laguerre bound. So in solid lines are the actual gap, and in dashed lines are these Laguerre bound. They are not. They are in this plot. They look on top of each other, but they are actually not on top of each other. You have to look at close, but they are very close together. But most important, they vanish in the same way. So you can compute the the dynamic exponent z, you get the log plot here, and you get the coefficient 1.5, and it comes 0, 0, 0, 0, and then some fluctuations. But it's 1.5 with high accuracy because you are going to assistance of exponential to 16 is 10 to the 7. So it's a chain of 10 to the 7 spins, and we are computing the mass gap exactly in 10 seconds. So this is just to show how this method is well, it's powerful, okay. And the eighth fortunate event is that the Laguerre bound has the same z as the actual dynamic exponent. And the Laguerre bound depends only on 3 coefficients. And these 3 coefficients, in Clay systems, I can do a little math, and I can compute it analytically. And that's the analytical solution, p plus 1 over n. So I get this dynamical exponent, which is, well, it depends on Pn, can be CFT, is equal 1. But can be many other stuff. As in Fendler's model, you get 3/2.
Question. So the fact that the z of the Laguerre bound is the same as the actual z, can you prove it, or you see it? No,
unfortunately, there are many. I try to prove that for clean systems, you see that it's not actual proof. It's a wave hand proof, and it comes as I said before. In critical systems, the finite size gap is vanished with L. So we compute the inverse, the roots of the polynomial is inverse of that. So there is a root of the polynomial that's divergent. But it is bounded by Laguerre bound. And it turns out the Laguerre bound, for all models that you have seen, they are diverging together with the same exponent. So this is one of an example of that. Don't have an actual proof for that. Okay, but I think the best application for this method is random systems. So let's go to the random transverse field is in chain. This slide is just a small review on this model. So you have random couplings and external transverse field. What are the phases of this model? Let's say that these random couplings are distributed as some given distribution, doesn't matter the actual shape of it. And let's say that the transverse field is here, larger than all the j's. So you're in the paramagnetic phase. All spins are aligned to the x direction together with the field. If all the fields are smaller than all the j's, you're in the ferromagnetic phase where there is two states. If you are in the middle, near to the critical point, the mass gap vanishes, and you end up in a so-called Griffith's paramagnetic phase, where there is no spectral gap in this entire region. So the dynamics is very slow, and we can understand why this dynamics is slow is due to the coherent fluctuations of these rare regions. This is a rare region where the couplings, local couplings, are bigger than all the j's, so they fluctuate coherently. It's just very slow, coherent, like Hoyos law that was discussing just moments ago. And the inverse of this time scale is the energy gap, which is vanishing exponentially fast with this rare region size. And they can be of any size, because it's just a matter of flipping coins and get. So it turns out that the gap is 0 here. So our method works better when the spectral gap is small. So it works very good in this entire region here. And that's what we have done. This is the critical point, and we have done experiments. These different colors are different points in the phase diagram, and we can compute the dynamical exponent for different points in the phase diagram in the Griffiths paramagnetic phase, and they are plotted here. We can add a field in the border of the size, a surface field, and we can compute the finite size corrections to the scaling, where ZL is Z infinite times some corrections to scaling. And we found by chance something that we don't understand. Although this is a well-studied model, we do not understand why the finite size corrections to scaling is so different, just adding a small surface field. And we go to system size that are very, very large, and we can see how they behave differently. So without surface field, you get a correction that is 1 over L, but if you add a surface field, this correction is exponentially small. So we don't have a theory for that, but just a numerical found. It is infinity at the quantum critical point, but we are not at, we are in the Griffiths, we are around here. So we are not exactly there. Yes, is this slide here. So there is actual analytical prediction for the dynamical exponent. It is the solution of this equation here, which means that when Z is very large, it diverges one over the distance from criticality, and this is the distance from criticality. So it's the difference between the geometric average of H and J. So this is the analytical prediction, and data points are our numerics. And we went computing dynamical exponent that is around 72 here, just to show that we can do that. All right, so if you go to the critical point now, Z is infinity, and actually what happens is that the finite size gap diverges exponentially fast with the system size with a universal critical exponent, and we found this. We plot here the distribution of this quantity eta here. So this eta is the log of the finite size gap divided by the square root of L, and it finds, it fits neatly some predictions. And this dashed line is a strong disorder normalization group, which is not exact, but has the correct scaling. Just to show you our computational time. So computing with Laguerre bound, it grows linearly, like this. If you compute the exact finite size gap, it takes a little bit of more time, but also growing linearly. And it's almost as good as the, so the exact is this one here. So, and the black one is a strong disorder normalization group, which is not exact, but both of them are growing linearly. So we are in good business. Okay, so last application is the to the Rundle-Fendley Rundle model. So you get coupling constants that now are random in space. And let me just explain our results. It will depend how this order couples to these coupling constants. If, for instance, this order couples generically to the free coupling constants, you have this phase diagram here, where you have gapful phases, A, B, and C. You have gapless Griffiths phase, which is the shaded area here. We have infinite randomness critical points, these dashed lines, and a multi-critical infinite randomness critical point as well. If this order couples only to one of these coupling constants, let's say lambda A, we have a different physics. this transition here between phase B and C, and B and C are not random. It's in the easy university class, then you enter a region of finite disordered fixed points where Z is finite, and then you reach an infinite disordered fixed point here where Z is infinity. So only in a single model. Since I have only 5 minutes left, I will just flesh out how our numerics work out. Is the following. So if I do 3 experiments here, I'm running up lambda b from here to there and keeping lambda a constants. I get this result from the of critical exponent z, which is diverging at the transition point. So it's diverging as in the Ising model. Is 1 divided by 2 times the distance from criticality. If I sit on the critical line at the chain A and chain B, I can see that the gap is diverging. This is log of log, and this is log L, so this diverges exponentially with the expected critical exponent psi 1/2. So is this trend here. The dashed line is slope 1/2. So if I sit at this multi-critical point here, I again get infinite randomness with the same psi, but different coupling, different constants here, but doesn't matter. It's psi 1/2 again. If I go to this multi-critical point here, also psi 1/2. So I can have all these good collapse. If I run the experiment from here up to the transition point, I get a finite size gap, as should be, because I'm in, I don't have Griffith's phases here. And that's where our method works worse, because finite size gap, then I have to use a long polynomial to find it. But it's not that bad, because I don't need to go to very big systems to find the correct finite size, to the correct finite gap. So I'm running from here to there. So for while I'm outside of the shaded area, I get z equal 1, which are these slopes. And when I enter this blue area here, z starts to change and increasing and diverges. With that, I will just flash my conclusions here. I hope to have convinced you that I had a method for compute the mass gap for free particle quantum systems that is most efficient for gapless systems with only computational effort of growing with the system size. This method works for free fermionic system without Jordan-Wegener transformation. We know the spectrum, but we know nothing about the correlation functions or the wave functions, because there is no transformation, just about the spectrum here. This is the new development on free fermionic systems. We have, for many years, we thought the free fermionic systems, you always have a Jordan-Wegener transformation that you map into free fermions. That's not true. We have, just showed you here that we don't have Jordan-Wegener transformation, but we still have free fermionic spectrum. I applied to this method to clean systems, so you can have an analytic prediction using the Laguerre bounds for the dynamical exponents. Apply that to the transverse field Ising chain, where new results for surface fields were found, and we don't understand that analytically. And I applied that for the random family model, which has a rich phase diagram with a clean finite disorder, infinite disorder, criticality, Griffith's phase, and all this stuff. Okay, thanks for your attention.
Time for questions. It's very inconvenient.
Yeah, thanks. Very interesting. So just to understand these free fermions without Jordan Wigner. So the quasi-energies are real numbers, and you can still choose the occupations to be 0 or 1 arbitrarily without. So it's completely equivalent to free fermions.
Yes, completely equivalent. And if you go to any larger than 2, the quasi-energy can be complex as well. So you have parafermions instead of.
Yeah. Let's stick to the one I think that you had that only had real. The Fenley model
Yeah,
only
N
had
equal
real.
2. N
Right?
equal 2.
N equals
N
2.
P. Okay.
But just to understand, so there is no Jordan Wigner, like literal Jordan Wigner, but there must be then some fermion creation operator, right? Or
Yes, correct.
so it's just that it's not known how to construct it, or?
There is this gentleman here. Let's come back. They use some graph theory to almost prove. It's not a mathematical proof, but it's very convincing that they show that there is no Jordan-Wigner transformation using graph theory to prove that. It's not a mathematical proof, but it's very convincing that it is. And I think in the field, nobody doubts that that's the case. So
But there must be like a fermion operator for each mode, right? Creation or.
There must be, but no one knows it.
Okay. That's very interesting, yeah. And in the more general case, these epsilons are complex, right?
Yes, that's correct.
And but then there are some restrictions on how you choose the W's so that the entire energy is real, or how does it work?
You mean the lambdas?
Yeah, the sum has to be real, right? So that it's.
Yes. No. This is not Hermitian.
It's not a Hermitian.
Yeah,
okay,
yeah, it's not Hermitian.
Okay.
Doesn't have this
Okay.
constraint.
You probably gave the answer when you mentioned that you don't know the wave functions, but there is a discussion about many-body localization going on. Intuitively, I would have said that you can almost prove that these models don't have many-body localization, but I don't know. Have you thought about it?
Yes. Well, this is free fermions, so shouldn't say anything about many-body localization because we need to break integrability somehow. But this somehow is still integrable because I can compute the quasi-energies with a polynomial cost, not exponentially cost. It would be nice to have a Hamiltonian that is many-body localized and apply here, but not in this model. This model.
I suspect it can't be almost, right? But it would be interesting to see whether one can prove this formally.
Yes. Yeah, of course. Yeah.
Yeah.
But I don't have this proof.
Any other questions?
So still related to the first question, you say that there is no Jordan-Wigner transformation. Does it mean that there is no fermionization in general? Maybe there is another fermionization mapping that you haven't explored?
Yeah, actually, that's what was, for instance, Fendley was putting forward, but I don't think he believes that anymore. So many people, even Marx in the beginning, thought there would be some fermionization, but since the 89, no one found any. And people in this field, StatMech field, they are looking for that very thoughtfully. But then came these Australian guys here, put forward this graph theory proof. It's hard to read, but it's convincing.
For your particular study, your results or methods or set sequence of fortunate events, do they really rely on these particles being having a fermionic nature? Because I couldn't see that. Where is really the dependence of this of these energies being from fermionic quasiparticles?
Yeah, it turns out to be fermionic because they are the solutions of this equation here. When you look for the solution of this, you see that this is the case. And then but this is exactly the fermion. But
Where?
here, these numbers S, they can be 0, 1,
okay.
and until n minus 1. So for n equal 2 is 0 and 1, just like the fermions. It comes out from the solution of this polynomial.
Parafermionic
In general, parafermionic. Yeah.
not fermionic in general. Parafermionic.
Yeah, n equal 2 is fermionic. Yeah, yeah. And from
okay,
that, we
I
say
see.
that these free fermions.
Okay.
From
Okay,
that.
now I get it.
There is no operator arising from there, like you're asking. There is no fermionization come out from it. It's just a solution of this polynomial.
Okay.
That's why I say that's the breakthrough on free fermionic systems, because we always thought free fermions as having a fermionic representation, a fermionization operators. It seems that there is a class of problems that's not the case. We can have that. We don't know anything about the wave function, but we know the quasi-energies.
Just a quick question: if there is a relation between the kind of polynomial and the kind of problem, a fermionic problem you have. So let's say you have let's say Chebyshev polynomials would be this kind of problem, and so on and so forth. Is there such a link?
Oh, these are the Chebyshev polynomials.
Yeah, sure. I'm just asking if this
Yes,
you change. Let's
yes.
say if change your problem. If you
Yeah,
find this.
yeah. You have generalization for other p's and other n's. You have generalization of the Chebyshev polynomials. Yes,
Okay, so
that's totally related.
You want?
So I just want to ask, if you have the conserved quantities, right? You have, it's an integral system. So does not this give you a hint of what would be your fermionic representation? It may be even no local, right? You just have,
Well, already in the easy model is non-local, right?
Yeah.
Because you have the string. It certainly is non-local.
but it doesn't have to be the same for every fermions, right? So you can have a transformation.
Yeah,
I
I don't know.
Every conserved quantity, it gives
Yeah.
you a different fermionic operator.
Yeah, I don't think so. We never found it. So
Maybe a related question is if you can write down the wave function in the spin representation of something that has some given occupation. Can that
have even occupation.
the given occupation,
given
the,
occupation,
the,
okay.
the occupation of the states, when you have an eigenstate, can you actually write down the wave function in spin representation, even if it's a sum of a lot of spins? Can it be?
Yeah,
is it
we
known?
tried that. Didn't go far. Sorry. Yeah, maybe you're not clever enough. But it didn't work.
Final quick question. The multi-critical point had psi equals 1/2. It could
Yeah.
have different.
I was hoping to have a different psi, but it's 1/2, unfortunately.
The other models will have it.
Yeah, maybe our models have 1/n, right?
Yeah.
But this one is always 1/2.
Okay.
And I have a SDRG for this entire thing, so I didn't put it here, but it gives 1/2. I understand why it's 1/2,
Okay.
but I don't have time to show it here.
Okay, so let's finish the morning session, or the first session of the morning, and thank José again. We have a short break.